This video is part of firm theory. In it, I will introduce production functions. A production function summarizes the various ways a firm can transform inputs into the maximum amount of output. For simplicity, we'll assume that output, or Q, is a function of only two inputs. By default, these inputs will be labor, L, and capital, K. Here, capital represents physical capital, not financial capital. Money is not an input. Money buys inputs that then produce output, but money itself doesn't create anything. Therefore, capital represents physical capital, such as machinery, tools, and computers. A production function shows the maximum amount of output that can be produced from various bundles or levels of labor and capital. As you'll see, production functions are a lot like utility functions. One big difference, however, is that production is cardinal. The numbers that come out of production function represent output and allow us not only to rank different output levels, but to make more meaningful comparisons. For example, now if output from bundle 1 is 100 and output from bundle 2 is 50, we can say not only that output 2 is bigger than output 1, but that output 2 is twice as big as output 1. Since production is cardinal, we can no longer monotonically transform production functions, like we did with utility functions. In this class, we will use 4 common production functions: the Cobb-Douglas production function, perfect substitutes production functions, perfect complements production functions, which now are called fixed proportion, and the quasi-linear production function. These should look familiar because they are a lot like the utility functions we saw in consumer theory. Production functions can be graphically represented by isoquants. An isoquant is a level curve of a production function and graphically summarizes the combinations of inputs that produce a specific level of output. Iso means same and quant stands for quantity. So an isoquant shows all the combinations or bundles of inputs for which output is the same. A lot of what you learned about indifference curves in consumer theory can be applied to isoquants in firm theory. For example, the farther an isoquant is from the origin, the greater the level of output. Isoquants for the same production function can't cross each other, and isoquants slope down because we'll assume that each input is productive in the sense that more labor leads to more output, and more capital also leads to more output, giving us a necessary trade-off. The more labor the firm uses, the less capital it can employ to keep output the same. Just like we saw in consumer theory, when inputs are regarded as perfect substitutes, the corresponding isoquants are downward sloping and linear. That's because for two inputs that are perfectly substitutable, the rate at which the firm can trade one for the other is constant. For example, a toll booth collector can always be substituted with one toll collecting machine. Maybe 3 bank tellers can always be substituted with one ATM machine. When 2 inputs are fixed proportion inputs, they have to be used together in a fixed proportion. These inputs can't be substituted for each other at all. For example, in the production of haircuts, for every 1 barber, we need 1 pair of clippers to go with it. You can add a second barber, but if he doesn't have a second pair of clippers to work with, you can't produce any more haircuts. The same holds true of pilots and planes, or buses and bus drivers. These are cases where labor and capital have to be used together in a fixed proportion to produce any output. Just like we saw in consumer theory with perfect complement goods, fixed proportion input production functions give us L-shaped isoquants. So we see through these two extremes that there's some variation in input substitutability. At one extreme, in the case of perfect substitutes, inputs can always be substituted at the same rate, and isoquants are downward sloping and linear. At the other extreme, in the case of fixed proportion inputs, inputs can't be substituted for each other at all, and instead have to be used together in a fixed proportion. In this case, isoquants are L-shaped. When isoquants are downward sloping and convex, that represents some intermediate case. Inputs are substitutable because the isoquants slope down, reflecting that there has to be a trade-off, but they don't slope down at a constant rate. We call these imperfect substitutes. Imperfect substitute inputs can be represented by Cobb-Douglas production functions, as well as some quasi-linear production functions. One measure of how easily one input can be traded for the other is the marginal rate of technical substitution. The marginal rate of technical substitution, or MRTS for short, is the absolute value of the slope of an isoquant and shows the ability of a firm to replace one input for another while holding output constant. Like all slopes, the MRTS is a rise over a run. Here the rise is the change in capital, because capital is usually graphed on the y-axis, and the run is the change in labor, since labor is usually graphed on the x-axis. Like all slopes, this is also expressible as a derivative, the derivative of capital with respect to labor. The MRTS will tell us how many units of capital the firm can replace with an extra unit of labor without changing its output. The formula for the MRTS, like the formula for the MRS seen in consumer theory, can be derived by taking the total differential of a production function. In doing that, we now have marginal products for each input. The marginal product of labor, for example, is the partial derivative of the production function with respect to labor holding capital constant. It tells us how much additional output the firm can produce by using one more unit of labor when holding capital constant. The marginal product of capital is the partial derivative of production with respect to capital, now holding labor constant. MPK tells us how much additional output the firm can produce if it uses one more unit of capital holding the amount of labor constant. It can be shown that the MRTS is the negative of the slope of an isoquant and equal to the ratio of marginal products, the marginal product of labor over the marginal product of capital, or more generally, the marginal product of the input on the x-axis divided by the marginal product of the input on the y-axis. Now, it can be confusing to think of a negative of a slope, which is why I define the MRTS as the absolute value of the slope. For example, suppose that at some point on an isoquant, the MPL is 12 while the MPK is 3. This makes the MRTS, since it's MPL over MPK, equal to 12 over 3 or 4 over 1. What does this mean? Well, even though I set up the MRTS as MPL over MPK, I interpret it as the change in capital for a change in labor. So 4 means that if the firm adds one more unit of labor, it has to give up 4 units of capital to keep output the same. That's because adding one more unit of labor increases output by 12 units. To keep output the same, therefore, the firm has to take away enough capital to bring output back down by 12. According to the MPK, for every 1 unit of capital that the firm gets rid of, output comes down by 3. So for output to come down by 12, the firm needs to reduce capital by 4 units. Note that the MRTS diminishes or decreases along a convex isoquant. That is, as the firm moves from C to D to E, the slope in absolute value gets smaller and smaller and smaller. We see then that the more labor a firm uses or has, the harder and harder it becomes to replace capital with labor.